let's talk about the first law of thermodynamics. So the first law of thermodynamics helps us understand what's going on with internal energy of a system, particularly a gas. So how is heat transferred to this gas converted into doing work? That's kind of a question we have. And the answer here is using energy conservation. So really the first law of thermodynamics is applying energy conservation to an isolated system, particularly a gas. So it states that the change of internal energy of a system is equal to the net heat transfer into the system plus the work done to the system. So in an equation we have this here. So delta U, so U here stands for internal energy, is equal to Q plus W. So Q here is the heat transferred into the system, and W is the work done to the system. So I like to kind of think of this as very similar to this diagram here, right? So here you have a magical box, that's our system, right? So adding heat to the system is going to increase the internal energy, right? So heat being added in increases internal energy, which makes sense, right? Because it's directly proportional to temperature. The internal energy, kinetic energy, I should say. Now, work done on the system is also going to increase the energy. But if our system does work, that's going to remove energy from the system. And it might also leak heat into the environment, right? So, and we can kind of then use this to compute energy changes. So a couple notes here about the difference between heat and work. So heat is not a very organized process, and it's driven by temperature differences, where work is very process and systematic. And it's basically dealing with the macroscopic force exerted through a distance. Right? Remember the formula for work being FD cosine theta? We're going to be using that here. So kind of some similarities between them is they both cause temperature changes. Though once the temperatures change, it's impossible to tell which caused it. So very similar to what we talked about lesson. These are both energy in transit, right? So heat's being added and removed, work added and removed, and it translates to a change in kinetic energy. So if we kind of take a microscopic view of what's going on with internal energy, right? So we're basically looking at this in terms of the atomic or molecular scale. Now, this is going to be a property of the kinetic and potential energy of whatever atoms are going on in there. So when I talk about U, the internal energy, I really mean the total mechanical energy of the system, kind of molecularly. Now, if we kind of try to take this microscopic level, it's kind of hard to deal with, right? Because we're dealing with molecules and atoms that are moving at different speeds and different average velocities. And it's very difficult to count the number of atoms in the system and account for this. So it's tedious and not always practical to compute internal energy of the system in this microscopic way. So this is where this first law of thermodynamics is helpful, because it allows us to determine the information about the internal energy, specifically the change in internal energy, which is all that's really useful, using these kind of macroscopic quantities of heat and work. So the internal energy really only depends on the state of the system, not how it reaches that state. So it makes it very much easier to deal with. So we do have also something here called path independence. I wouldn't really necessarily worry about this too much, but this is actually, it's kind of similar to what we talked about last year when we dealt with conservative forces. But basically this says that if we have some amount of internal energy for our system at one point in time, and then it changes to some other internal energy, that change in energy is going to be the same no matter what caused that change. So basically that means if the system changed energy, let's say it increased in energy by, let's say, 12 joules, all we won't be able to tell how it got to that point. We could have done work on this system to increase its energy up to that value, or we could have added heat to do that, or we could have done both. All right. There's no way for us to tell how that happened, and it, for the most part, doesn't really matter. Now we can compute the change in internal energy. So let's look at this example here. So let's suppose that we have a heat transfer of 40 joules to a system, while the system does 10 joules of work. And then later, the heat's transfer of 25 joules out of the system, while 4 joules of work is done on the system. So the question here is, what is the net change of energy of the system? All right, so I did this math by kind of drawing that box method again. All right, so we're told that we've got 40 joules of heat transferred into the system, while we've got 10 joules of work done by the system, so that's a negative quantity. While we also have 25 joules of heat loss and 4 joules of work done on the system, meaning 4 joules of work is added to the system of energy, I should say. So kind of overall, we can, add and subtract here and find like overall that the change in work is going to be negative 6 joules and the change in heat is positive 15 joules. So using our first law of thermodynamics, we end up with 15 joules minus 6 joules giving us 9 joules. So our change in internal energy is a positive 9 joules. So overall, the system has a positive increase in energy of 9 joules. Now, if we instead had the system have a total amount of heat removed from the system of 150 joules and 159 joules of work done on the system, we again have the situation here where we have a positive 159 and a negative 150 giving us a total change in internal energy of 9 joules. So the question then is, part C, if we only knew the final energy state of each system, meaning we knew only that they both increased by 9 joules, could we tell these two systems apart? And no, we couldn't. We couldn't tell what process it went through. Whether it went through process A or process B, we wouldn't be able to tell. We only know that the energy changed by some amount. All right, so let's focus on work a little bit, how we can visualize that or use that in our systems. So a couple of assumptions we're going to be using. So we're going to assume that our system is a gas. And not only that, but the gas is an ideal gas that's in thermodynamic equilibrium, meaning that the gas has equal temperature throughout the gas and it has the same pressure throughout the gas as well. For simplicity's sake, it's going to be easy to imagine what's going on in terms of what I mean by doing work on, or the system doing work, by imagining a gas cylinder. So a gas cylinder would look something like this. So it's some sort of container where we have a gas in it that occupies a certain volume and has a certain pressure. Typically, we're going to have some sort of piston acting on this system, and this piston exerts a force on this gas, and it can change the pressure and volume of the gas itself. So thinking about what can cause the piston to move or accelerate, well, that'd be some sort of external force, which would mean that we have a pressure difference from outside the container to inside the container. Now let's assume that we're dealing with some constant force being applied that's going to slowly compress the gas. So this reason why I'm saying it's slow is that means that our gas is able to stay in thermodynamic equilibrium. If we have fast compression, things get a little wonky, and that doesn't happen. But nonetheless, we'll compress it slowly. So let's kind of come up with an expression here. So we'll derive an expression for the work done on the gas, considering we know the information about the pressure and volume. And naturally, I left my notes at a different location. So I guess I'll stop the video here and we'll start with this derivation in the next video.